Second order dynamics are times when our processes will begin to behave interestingly. They'll begin to oscillate about a point potentially depending on the characteristics, and we may examine behaviors such as overshoot and decay ratios, and so things do get a bit more complicated. And so what I'm going to do in this video is introduce the frequency domain of second order dynamics, and then we will make an example of how to go from the frequency domain with a unit step input to a time domain, so we can examine and visualize what these kinds of second order processes look like if you ever come across one. And so the first thing we're going to do is distribute our denominator of this equation to realize we'll have tau 1 tau 2 s squared plus tau 1 plus tau 2 quantity times s plus 1, and we're going to divide it by the numerator, or the numerator will go on the top, tau a s plus 1. And once you have it in this form, we can begin to dissect it a bit and realize that commonly in textbooks you'll find second order dynamics written in this notation, where we have g of s is equal to tau a s plus 1 divided by tau squared s squared plus 2 zeta times tau plus times s plus 1. And we introduce this zeta term, which is referred to as a damping coefficient, and an overall time constant, as well as this numerator time constant. And so where our process will get interesting is if we find that zeta is greater than 1, we have an overdamped system. And in that case, we observe no oscillations. If zeta is equal to 1, it is called critically damped. And we again observe no oscillations, but we're on the verge of doing it. And then if zeta is less than 1, and also greater than 0, so it's still a physical system, we say our system is underdamped, and we observe oscillations. And so if you're given a process transfer function in this form, you can derive what zeta is. We can determine if we should expect oscillatory behavior. And in addition to that, if tau a is greater than tau, we have overshoot. And in my next video, I can get into what these terms actually are, but this is just an introduction to the core concepts. And so to kind of spell it out, we can see visually here what tau squared is equal to. So tau squared is equal to tau 1 times tau 2, and then 2 zeta tau is equal to tau 1 plus tau 2. So if you have numbers, we have two equations with two unknowns, and we can evaluate what tau 1 and tau 2 are to put everything back into this kind of nice notation. But for the sake of just introducing these core concepts, these are what we're working with. And so figuring out what zeta is very important. Figuring out if you have tau a that is greater than tau, you'll see overshoot is also another very important concept that we'll get into. And this wraps up the second order dynamics. Thanks for watching. Let me know if you have any questions.